Hello, we are from NJIT and we are from Department of Computer Science and our subject is IHLP. Now we are going to present on a topic called making middle boxes someone else's problems in that network processing as a cloud service. And we are team of three, myself, Kaivalya, and my friends are Fani Verma and Sushant Reddy. First of all, we'll look into what is middle box. Here, the middle box is nothing but it is a computer networking devices that transforms, evaluate, and filters and performs some other operations on the data for its uses. And everything, all these are included except the packet forwarding. All this process is known as middle box. It is also known as network appliance. And the middle boxes are specialized appliances that are widely used in the enterprise networks to improve the security, performance, and reduces the bandwidth of the systems. And there are a few examples of middle boxes, which includes the firewalls, instruct detection systems, and proxies, and WAN optimizers. Next, the middle boxes today. It tells us how the middle boxes has been using nowadays. Here we can see the graph. It gives the how much we are spending on the middle box hardware per network. As you can see, it displays the 5 years expenditures on the middle box hardware against the number of actively deployed middle boxes in the network. And on the y-axis, we have the number of middle boxes, and on the x-axis, we have the expenditures from the past 5 years in the dollars. The survey on very large networks and small and medium networks. For the very large networks, they spent over the $1 million on the middle box hardwares. And on the middle and the small networks, they spent around $5,000 to $50,000 from the past 5 years. And next, it is it this graph is different from the previous one. This gives the number of personnels per the network, and it displays the estimated number of personnels and the middle box per the network. And you can see that on x-axis we have the number of middle boxes, and on y-axis we have the number of personnels. It gives the number of personnels required to manage the middle boxes increases with the number of middle boxes deployed in the network. From the result of this graph, majority of the networks required fewer than the 100 personnels to manage their middle boxes for the better usage. Next, let's go to the middle box deployment. Here we can see the bar plot of the middle box deployment. This here we have taken large, small, medium, very large networks. And on the x-axis, these are present. And on the y-axis, we have the log scale from 1 to 10,000. And you can see here the lavender color represents the small networks, and the medium represents the blue one, and the green represents the large networks. The red represents the very large ones. Here, the enterprise networks are a complex ecosystems of the firewalls and IDs and web proxies and other devices. The box plot gives us the number of middle boxes deployed in a network for all the sizes, which are from medium, small, large, and very large, as well as the number of routers and the switches for the comparison. And the number of middle boxes in the network is equal to the number of routers and irrespective of their network size. Here, next, let's go to the middle box deployment. The average very large networks in the data set host around 2,850 L3 routers and 1946 middle boxes. The average small networks in the dataset host 7.3 L3 routers and 10.2 total middle box. In addition to this, these are some of these included, which are the hardware cost and middle box deployments comes with the significant operating cost and large management terms, and a wide range of skills are required to manage these multiple heterogeneous devices. Next, Let's go to the complexity in the management of the middle box. It provides the breakdown of the management task related to the middle boxes. It also includes the upgrades and the vendor interactions, which entails deploying new hardware infrastructure and with the negotiating with the vendors. The purpose they propose is a practical solution for this complexity, which is Aplom, which is appliances for the outstanding outsourcing middle boxes that outsources the middle box processing to the cloud, reduce the complexity, and it will also reduce the cost managing for the middle boxes. Next, here is a table for the common cause of middle box failure. In the middle box failure, the most common factors are the misconfiguration, overload, and physical and electrical failures. Here, in the table, there are three types of middle boxes, which are firewalls, proxies, and IDs. And there are three different types, which is misconfiguration, overload, and physical and electrical problems. For the misconfiguration, the most common cause of the failure, of all the three types of middle boxes, the most common cause of the failure is which is nothing but the misconfiguration. Here you can see 67.3 percentage of the network administration estimates that most common cause of the firewall failure. And for the proxy failure, they estimate 63.2 percentage as the most common cause. And for the ID failure, the most common cause, which estimated is 54.5 percentage. Now let's go to the overloads and failures. The overload and physical and electrical failures are significant cause of the failures for different types of middle boxes, with roughly around 16% to 34%. They estimated the most common cause for the failure of the middle boxes. Next, let's look into the ratios of the average peak activity, active connections for all the proxies, firewalls, and load balancers in very large enterprise. Here on the x-axis, you can see the average and maximum observed active connections. And on y-axis, you can see the cumulative fraction of middle boxes. Here, the proxies are represented in the red one, and the firewalls are represented with the black ones, and the load balancers are represented with the blue color. Next, from the above graph, here are the few points, which is the proxy has the highest ratio of average to peak active connections with a median ratio of 0.6, and the firewall has a median ratio of 0.4. And let's go to the load balancer. It has a median ratio of 0.3. The ratios are very important here because they affect the capacity planning of middle boxes, and the middle boxes must also provide to handle the peak load if the ratios is high, which could cause the excess resource waste. And the middle boxes can also be provided to handle the average load. If the ratios are too low, then it will result in the cost saving. Here, the problem can be solved with the help of the cloud-based solution like Aplom, which allow on-demand scaling. Next, my friend will continue this topic, design space.
Hello guys, myself Fani Verma. Now I'll continue with this topic, design space redirection. Firstly, design space redirection has three natural approaches for redirecting the traffic to the cloud for middle box processing and analyzing the latency versus complexity traits. In this design space redirection, we have three approaches. As we see here, one is bound redirection, another one is IP redirection, and third one is DNS redirection. Simply design space redirection means we can say that it applies on internet, means like we can say using the clever design to guide people's where want to them to go website or app, like prompting them to go click on button like that to explore specific areas. We use this design space redirection. So in this design space redirection, now we can see the first one, like bounce redirection is the first redirection. We use some simplest case. Yeah, here we can say bounce redirection is the simplest case where Aplom gateway at enterprise tunneling both ingress and egress traffic to the cloud, and incoming traffic is bounced to the cloud POP and processed by middle boxes, and then it's sent back to the enterprises, and outgoing traffic is similarly redirected. Here we have the simple picture for bounce redirection. Yeah, here we can see that external site means which is called internet will pass the data. Like here we have two data. One is tunnel and another one is encrypted data. And from there again we will get to the cloud providers, and again that cloud providers will send back to the Aplambo gates. Like that the whole process will done, and this process we can call it as bounce redirection implement latencies. And coming to the next one, we have another case called IP redirection. Here, IP redirection means it involves the tunneling traffic to and from the cloud POP, which is different from above case, which it has the minimum RTT. Here, RTT means we can say round trip time. Here we have the another picture for IP redirection. Here we have same external side, which is internet. From there, the data will passes, like we have two types of data. One is tunnel data, another one is encrypted data. This data travel through cloud east, and then it will go to Aplambo gates. Again, it will forward to the back to the internet side. This whole process we can say it as IP redirection, and this diagram refers to the IP redirection in multi-pop deployments cannot be ensured in the bidirectional traffic transfer. Next slide. Yeah, and we have last most one is DNS redirection. Here DNS redirection is based on the enterprise tunneling traffic to and from the cloud POP, to which it has minimum RTT like round trip time based on the DNS resolutions. And also we have here clear picture that same again it includes the external site, which means internet, and we have cloud providers, and we have the Plomo gates and enterprise. But here we have small difference. The data will transfer through the cloud provider, which is different from about two. And from same we have two types of data. One is tunnel and another one is encrypted. But here there is a small change. This data will transfer through the cloud providers, and then it will go to the external sites and DNS redirection. So this whole process we can say it as DNS based redirection. Yeah. And coming to next one, it is minimizing the latency. Here, minimizing the latency means the DNS redirection is choose in the system architecture because it avoids the latency penalty of bounce redirection and provides more control over the redirection than pure IP address. Same, it has two types. One is smart redirection, which is different from above three, and also we have another one, provide footprints. These two are the minimizing the latencies. Now we can go through these two. Yeah, here we have the chip, and coming to the smart redirection, it redirects the traffic not through the cloud POP because it not transfer the data through the cloud POP because it has minimum RTT to and from the enterprise, but it redirects the traffic on per destination basis through the POP that minimize the end-to-end latency. This is called smart redirection. And the second one is provide footprint. This provider footprint analyze the middle box provider choice of geographs, footprints, and impact the latency. And it concludes that while a larger footprint provides a lower latency, and it is not clear how large a footprint is required in the context of the outsourcing middle boxes. And next one will continue by my one of my teammates, Shishant Reddy.
Yeah, I'm Sushant, and now I'm going to explain about Aplom detailed design. So the Aplom design architecture consists of three components: the Aplom gateway and the corresponding functions and middlebox capabilities at the cloud provider, a control plane responsible for managing and configuring these components. Uh, so here is the architecture components of Aplom. So this component is responsible for redirecting enterprise traffic. It's like a traffic manager that ensures data from the enterprise networks and takes the most efficient part to the cloud. And the cloud provider is hosted by the cloud and encompasses the necessary functions and capabilities uh, for the cloud instances. And the Aplong gateway, it logically co-located with the entire with the enterprise gateway router and two key functions: maintaining persistent tunnels to multiple cloud POPs and steering the outgoing traffic to the appropriate cloud POP. The gateway registers itself with the cloud controller, which supplies it with a list of cloud tunnel endpoints in each POP and forwarding rules for redirection and cloud functionality. The cloud provider has three main tasks: providing public and private IP addresses to the enterprise customer, and applying middle box processing services to the customer's traffic according to their policies, and tunneling traffic to and from the appropriate Aplong gateways at enterprise sites. And the core components are tunnel endpoints to encapsulate and decapsulate traffic from the enterprise, and middle blocks instances, which is used for processing the customer traffic, and NAT devices to translate between publicly visible IP addresses and the client's internal IP addresses, policy switching logic to steer packets between the above components, and control plane. The control plane oversees and manages the entire system. It's like the brain of Aplom, responsible for configuring and coordinating the actions of the gateway and cloud-based functions. It ensures everything works in harmony. Uh, and the control plane has three functions: redirection optimization, which pushes the current best tunnel selection strategies to the Aplong gateway gate by using measurement data from the cloud POPs, and policy configuration. The cloud provider provides a rich policy configuration interface that exports the available types of middle block processing to enterprise administrators, and also implements a programmatic interface to specify the types of middle block processing required. And the middle block scaling detects changes in utilization using data from the heartbeat health checks to automatically scale out or scale in. The implementation. Aplom describes an implementation as a modular system consisting of three major components: the Aplom gateway, the cloud POP, and the control plane. And it also acts as a software architecture diagram of their implementation. And the Aplom endpoint software can be deployed on a standalone software router or as a tunneling layer on an end host, and installing and running the ends or software is as simple as connecting to a VPN. The performance benchmarks for common applications using the Aplom implementation, including HTTP page loads, BitTorrent, and voice over IP, and finds that this application experience minimal to no degradation when the traffic is redirected through Aplong. This underscores the effectiveness of Aplong in maintaining high quality user experiences according a range of applications. And this is a software architecture of Aplong, where the Aplong gateway is the key component for redirecting enterprise traffic, and the cloud controller oversees and manages the entire system. Evaluation: application performance. Aplong assesses the performance of three key applications: HTTP page loads, BitTorrent, and voice over IP, and finds that these applications experience minimal to no degradation when the traffic is redirected through Aplong. And the scaling and failover. Once a new middle box instance has been allocated and initialized, actual switchover time to begin routing through traffic it is less than 100 ms. And the conclusion: Aplong addresses critical challenges in enterprise networking by effectively outsourcing middle box processing to the cloud. This strategic move elevates key issues associated with the traditional middle box infrastructure, including high cost, complex management, inflexible capacity, and potential failures. By successfully offloading the majority of middle boxes, Aplong ensures optimal performance without compromising scalability or affordability. This innovative approach makes advanced middle box processing accessible to enterprises of all sizes, making a significant advancement in network efficiency and cost effectiveness. So by this, we will conclude our presentation. Thank you.